Welcome to the fourth lecture on statics ME106, and today we're going to begin with this new chapter on friction, which is chapter number 8. Uh, and before I begin with this chapter, let me remind you about the support reactions that you studied in chapter number 5 and probably chapter number 3. Uh, so you see that these supports are basically used to maintain the equilibrium of rigid bodies, and while they can block some of the degrees of freedom, they can actually allow others as well. So uh, so how these support reactions do this, uh, as soon as the external force or load is basically being acted on the rigid body, these supports will going to start exerting a reaction force or maybe reaction moments. So they work on the principle of Newton's third law. As soon as you will remove the external loading, you will see that these reaction forces and moments will going to vanish. But they are very important concepts in statics because they are able to keep your body in equilibrium, and they allow certain degrees of freedom while blocking others. And so friction is basically a reaction force, right? So it is also a reaction force, and the purpose of friction is to resist the motion between two contacting surfaces. So you see that the word impending here actually means that the motion is about to take place, because remember we are actually dealing with the statics. So the word impending motion here means that the body will be on verge of having motion. It is not in motion, but it will be on verge of having motion. So that motion will be restricted by the friction force, which is a reaction force. And so you see that this friction force or this reaction force actually occurs because of roughness, okay, present between the contacting surfaces, or maybe some sort of an adhesion due to some chemicals or contaminations, and possibly some sort of deformation taking place at the interface because of the applied loads. These are basically the causes why this friction force will going to appear. And you see that this friction force will always uh, be tangent or parallel to the contacting surfaces, and it opposes the direction of motion. So for example, if let's say this car is actually traveling in this direction, moving in this direction, and suddenly brakes are being applied, then right at the interface of the tire and the road, there will be a friction force whose direction will be opposite to the direction of motion of this body. Okay, and it is, you can see that it is in the opposite direction, so it is opposing the motion, okay, the impending motion of the car in the forward direction. And this is basically parallel or tangent to the contacting surface. So remember that friction force is a reaction force which will going to oppose the direction of motion, and it will be applied tangent or parallel to the contacting surfaces. Now there can be some advantages of friction. For example, there are machine elements like clutches, brakes, jigs and fixtures, clamps, belt drives, screws, wedges. So they all need friction force for their proper functioning. And also you have realized that we are basically able to walk because of the this friction force acting between our feet and the ground. And sometimes this friction force is also helpful in keeping the equilibrium, in maintaining the equilibrium of the body. For example, here if you see this wooden shaft, okay, its weight is basically acting in the downward direction. So because of its weight, it might slip. slip down. But the friction between this roller and these blocks, these yellow blocks, okay, at these contacting points, these friction forces are basically holding this wooden shaft in equilibrium. So sometimes these friction forces are really helpful in maintaining the equilibrium, or they are basically helpful in design of such fixtures and clamps. And so ultimately these friction forces will also going to have their effect on the associated mechanism and structure, and you need to find out the effect of these forces on structures as well. So similarly, in manufacturing processes like friction welding, rolling process, forging process, or grinding process, as shown in this slide, metal cutting processes, friction is always required. It becomes of fundamental importance. And then there can be triboelectric generators. You see, so the triboelectric generators, they are basically a device that works on the principle of friction when it exists between two dissimilar materials. So when two dissimilar materials rub against each other, they produce some static charges, and that can be utilized. So the underlying principle is the friction in triboelectric generators. But you see, friction can be very important, so much so that it can be a life-saving force, as you can see in this figure. On the other hand, it can have some disadvantages as well, because you see, most of the time in thermodynamic machines like engines, hydraulic turbines, gas turbines, steam turbines, compressor pumps, which are basically work consuming or work producing devices, you do not require friction there, because it can generate heat and a lot of rubbing action. It can generate wear, and it can bring down the efficiency of these thermodynamic machines at a lower level, which is not required actually. So there are certainly disadvantages of friction as well, and you can see here in these figures that there is a wear, because of the friction force. A wear is shown here on the cutting tool of a lathe machine, uh, and here you can see the effect of wear on a piston, automotive piston. So whenever metal to metal contact takes place, and the relative motion take place, there is always a chances of wear. So this is an adverse effect of friction, and in these kind of situations, you need friction to be minimized. So we see that in reality, no surface is smooth, and it might contain micro irregularities or micro roughness features at the interface. Okay, and so these micro irregularities or roughness features can cause interlocking effect, which results in the friction. So it is fair enough to say that friction force is basically a model force that mechanistically models the effect of micro irregularities and roughness between the contacting surfaces, right? So if you are involving friction in your static analysis, in your equilibrium analysis, this means that you are really you know you cater for the micro irregularities and roughness that happens to be there between the contacting surfaces. And so it's an important force, a model force. uh, so as you can see in this figure that these micro irregularities or micro roughness features between the contacting surfaces can be infinite actually in number. Okay, so at each and every contacting point there will be a normal reaction. As we know that whenever two bodies comes in contact, there is always a normal reaction at the interface. So whenever these two micro irregularities, acting at different interfaces, will come in contact with each other, uh, there will be a normal reaction. Okay, and because of these irregularities and roughness, the interlocking effect can take place, and so there will be a parallel or tangential uh, friction force, right, acting at this point. And you can see that these can be infinite in number, because these delta f and delta n can be infinite in number, because there are infinite uh, contacting points between irregular surfaces. And so you see that these infinite numbers of delta n and delta f actually creates or generates a distributed system of force, you know distributed system of force at the interface. So we can roughly represent a distributed system of forces like this. So there are infinite numbers of delta n acting at the interface, and there are infinite numbers of delta f. Okay, so this distributed loading basically constitute or makes a distributed loading diagram that happens to have some kind of an area. As you can see that this area resembles a trapezoid. So this distributed loading is basically taking place in form of a trapezoid, roughly in form of a trapezoidal area. And so as long as we are dealing in two dimensions, we assume that there is no variation of delta n into the screen. Okay, so into the screen or into the board, there is no variation of delta n, but delta n and delta f can vary along the length direction, like this. As you can see that the dimensions, the size of these arrows are different. So these micro irregularities basically generates infinite numbers of delta n and delta f, which in turn actually uh, generates a distributed system of forces. And we know that every distributed system of force can be converted into a resultant force, because this is what we do in statics. Remember, in statics, either we are trying to sum all the forces or group all the forces and calculate their resultant effect, or sometimes we need to distribute the resultant into its components acting in various directions. So this is the key feature of statics. It enables you to do this. So this distributed system of force delta n can be converted into a single resultant force capital N, shown here like this. And similarly, this system of parallel tangential forces delta Fn can be converted into a single resultant force F. Okay, so they are all collinear, therefore they are just the sum. So this F is just the sum of delta Fn's. And the the location from where this capital N will going to pass, it is basically the centroid of the loading diagram. So you see that this loading diagram resembles a trapezoid. It must be having some kind of a centroid that can be calculated using formulas, and from this centroid the resultant N will going to pass up. Okay, so you see that this N is basically passing from the centroid of this loading diagram, trapezoid. It is not passing from the center of gravity of this object. So from the center of gravity of the object, only the weight will going to pass. And this delta n, the location of this resultant force n, normal resultant force n, will depend upon the shape of the loading diagram. Okay, so this can be very irregular as well. If it is a very irregular distribution, then we need to use integration. But for simple shapes, we have formulas available for the centroid, and we can locate the centroid of these loading diagrams, and we can locate the direction of n. So this n here is basically passing at a distance x from the center of gravity of this object. That is why this n is shown at a distance x. This is the main reason that I wanted to tell you, because this resultant n is basically passing from the centroid of the loading diagram, not from the geometric center or center of gravity of the object. So it is at a distance x, and this f is simply the resultant of all delta fn's. So this is how we model the normal reaction at the contacting point of irregular surfaces and the friction force. Now, when this force P is applied on this body, okay, here, you see that this applied force can have two kinds of effect. So either this force can simply slide this object along this surface, okay, or it can tip the object over the surface. Now tipping means that this box will going to turn over or topple over the surface. For example, it will be something like this. This force can do something like this. So you see, this force can actually cause this box to topple over, tilt over or topple over from this surface. This is known as the tipping effect. So this applied force can either slide this box simply in this direction, okay, over the surface, and it can basically cause tipping. It can cause tipping effect. So it can tip over this box, and it can also slide this box. That depends upon one thing which I am going to tell you. So you see how you will going to identify that when the applied force will going to cause tipping of the object of your rigid body, or it will just simply going to slide. The key is that you notice the physical dimension of your rigid body. Okay, as you can see in this diagram that there is no dimension assigned to this box, no dimension assigned to this box, and therefore I have actually simply put a normal reaction n here, okay, and that is passing from the center of gravity of this object, because this case is actually smooth, so there is no friction force acting, there is no distribution of parallel forces like delta n, and so you can apply just simply one normal reaction in the upward direction. So the key feature is to note that there is no physical dimensions specified here in your object. When this is the case, we simply ignore the effect of tipping, and we say that the applied force can only slide the object. But as soon as the physical dimensions are given to you and the location of the force is also given to you, you at once realize that the situation now demands to check the effect of tipping as well. So as you can see in this diagram that physical dimensions of this rigid body is given to you, right? So this dimension is A, and this dimension is also probably A because it's a square, and so the center of gravity will lie at A by 2, and at this point the weight of this rigid body, this box, will going to pass, and now this n is shown at a distance x from the center of gravity of this object. So this distance x is the centroid of the loading diagram. This means that uh, now we have to show n at a distance x uh, from the center of gravity of this object, or now the n is basically passing from the centroid of the loading diagram, right? This is because now the physical dimensions are specified, and there is a probability that this force can basically cause tipping action. So then how it will be confirmed that the applied force will cause tipping action or it will going to cause sliding action? The point is that you will going to calculate the moment about this point O. So as soon as you will apply the equation of moment about this point O, you see that the normal reaction N and this reaction friction force F will not going to create any moment about point O because their line of action is passing from O. So the only forces left are W and P. These will going to create moment about point O. So you see the moment arm of W is X measured from point O, and this is actually a anti-clockwise movement, whereas the moment of P about point O is clockwise. So these two moments will try to balance each other as shown here. And from this equation you find out the value of X. So the value of X comes out to be PH over W, and you realize that normally these parameters, okay, this P, H and W are actually given to you. So normally you know what is the value of the applied force, you know what is the weight, okay, and you know the location of the applied force, and you can estimate X. Now how, once you get the value of X, you can decide that whether this applied force will going to cause sliding of the object or tipping of the object. So you see that if X comes out to be equal to A by 2 or some value that is greater than A by 2, okay, you say that the applied force will going to cause tipping of the object. And if this value of X comes out to be less than A by 2, we say that the applied force cannot cause tipping, but it can only cause sliding. So you see why I'm saying this, because as soon as the body is about to tip over, you see that this all point of contacts are basically they are no longer valid. Okay, the body is no longer making contact with the ground except at just one point which is acting at a distance A by 2. So this normal will going to shift itself at this point. So this normal will going to shift at this point when the body is just about to tip over. So from this point, which is the centroid of the loading diagram, the normal reaction will just move at just one point, which is the contacting point between the body and the surface, just at the point where the tipping is taking place. And this is why I say that if X, calculated value of X, is equal to A by 2 or greater than A by 2, you say that the applied force will going to cause tipping instead of sliding. And if this value of X comes out to be less than A by 2, we say that the applied force has a tendency of just causing sliding. So there are two possibilities whenever a force is applied on an object. Okay, it can either cause sliding and it can either cause tipping. And you see both of these effects will going to take place when the applied force is capable of exceeding the friction force, right? If it is larger than the friction force will not be able to maintain equilibrium, and therefore any one of these effects will going to take place. Either the body will going to slide or the body will going to tip. So when the physical dimensions are given to you, you have to check both the conditions, sliding and tipping. If the physical dimensions are not specified, then we rule out the possibility of tipping, and we say that the only condition that is required to be checked is the sliding. So this is a very important point, and I hope that you will going to remember this. So the key is that you look at the physical dimensions of your problem. If physical dimensions of the body is given to you, then it means that you have to check the condition for tipping. If it is not given, then you don't have to bother about tipping. So you see, as I mentioned that this friction force actually keeps the body in equilibrium. It tends to keep the body in equilibrium. Therefore, these friction problems can be best defined on the basis of regimes of motion. Okay, so referring to figure number 1, you see that uh, this normal reaction n is shown at a distance x. Okay, and this friction force is shown here. Okay, since the physical dimensions are not given, we are now ruling out the condition for tipping, and we assume, we say that this force P, we're only going to create sliding of this box. Okay, so if you apply submission of Fx on this system, the given system of this forces, if you apply submission of Fx equals to 0, this is an equilibrium equation. What result you will going to get? You will going to get that P is equal to Fs. P is equal to Fs. So as if you increase the value of P, what will going to happen? If you increase the value of P, what will going to happen? The value of Fs will also going to increase accordingly. So if this P increases, this Fs also increases, and that is why this straight line is given here. So if P increases, F increases. Now what happened? You have started to apply a force here, and you are assuming that the interface is not smooth, so there is a friction force resisting the motion. Okay, and there is a normal contact force here. Now you are increasing the value of P, then according to the equilibrium, summation Fx equal to 0, this Fs will also start to increase. And what happened that while it starts to increase, it is going to reach a point which is very important to understand. So let's say that this force F reaches a point, this red point here, where the value of F becomes equal to mu s times n. So this is Fs. At this point, the value of friction force becomes equal to mu Sn, and this is the maximum friction force. This is the limiting value of the friction force, or we say it is the maximum value of the friction force that can take place. Now, if you still try to increase the value of P at this point, what will happen? That the friction force, because it has already reached its maximum value, it will no longer be able to keep the body in equilibrium, and your body will be on verge of motion. Okay, the motion will just start to happen, and once this force is increased further, your body will be in motion. And so as soon as it'll be in motion, the force of static friction will start to drop, and it will become the force of kinetic friction, which is equal to mu kn. And that is why this graph is basically dropping, because force of kinetic friction is smaller than force of static friction, because once the body starts to move, it is easier for it to keep moving, and therefore the force of kinetic friction is smaller. So from this graph we understand that below this point, okay, below this point, this red point, which was the critical point, maximum point of friction force, your body remains in equilibrium. So this is the equilibrium region, static equilibrium. Your body remains in static equilibrium. As long as your friction force remains below this point or below its maximum value, your body is in equilibrium. As soon as the friction force reaches this red point, your body is on verge of motion, and that motion can be anything. It can be sliding or it can be tipping. So it is on verge of motion because the friction force has reached its maximum value at this point, and this point is known as the impending motion point. So at the impending motion point, the value of friction force is maximum, and that is given by this product. I will come to this product later on. So for now, you just remember that when your body is on the impending motion point, okay, the value of friction force is maximum in your system, and at this point the body is just on verge of motion, or you can say that its equilibrium is just about to disturb. And once it has entered into the motion regime, it will keep on moving, and the force of friction will no longer be static force of friction, it will be a kinetic force of friction. So below this point, everything is in equilibrium. Therefore, as far as the statics is concerned, this region and the impending motion point, these 2 points are the most, or these two regions are the most important region for our analysis. Okay, because we really are interested in finding out that whether our rigid body will going to remain in equilibrium or it is just about to move. These are the two important questions that we need to answer while solving problems in friction. Okay, so just a little formula derivation here. If you see that this is the normal reaction N and this is the friction force, so this Rs is basically the resultant of this N and F, and this N and F are basically the rectangular components of Rs. So from this right angle triangle, we can say that this phi S is equal to tangent inverse of this perpendicular, which is equal to Fs, and the base, which is equal to N. And we know that Fs is the maximum value of friction force, which is given by the product of mu s n. So you substitute in place of Fs mu s n and you get this result. So this phi s is known as the angle of static friction. Okay, and this angle of static friction is equal to the tangent inverse of coefficient of static friction. This mu s is known as the coefficient of static friction. So what is the coefficient of static friction? Mu s is the coefficient of static friction, and this actually is a measure of degree of roughness between the mating surfaces. So this mu s actually tells you how rough uh, the contacting surfaces are. It purely depends upon their roughness, or you can say it purely depends upon the material of the contacting surfaces, and it can only be experimentally measured. So here you can see a table, and here I have shown you some values of coefficient of static friction. Metal on ice has 0.03 to 0.05. Wood on wood has coefficient of static friction as zero point 0.3 to zero point 0.7. Leather on wood 0.2 to zero point 0.5. Leather on metal 0.3 to zero point 0.6. And metal on metal highest. This will produce lot of friction force and lot of wear. So mu s actually depends upon the value of sorry, the type of material, uh, the condition at the contacting surface, the roughness condition of the contacting surface. Now come to this formula, Fs equals to mu s n. Please remember that this equation Fs equals to mu s n is not an equilibrium equation, because we have only learned three equations of equilibrium in two-dimensional problems. Okay, number one, submission Fx equal to 0, number 2 submission Fy equals to 0, and number 3 submission of all moment equal to 0. These three are the equations of equilibrium in two dimensions. Of course, if you are dealing with three dimensions, then you have six equations of equilibrium: submission Fx 0, submission Fy 0, submission Fz 0, submission of moment about x axis 0, submission of moment about y axis 0, submission of moment about z axis 0. So for two-dimensional problems, we have three equations of equilibrium. And so this equation Fs equals to mu Sn is not an equilibrium equation. It is purely an empirical relationship. Means that it purely depends upon the observations, experiments. Okay, and there is a concept behind this formulation. You see, assume that you have a body here which is basically in contact with a rough surface, and the weight of this object is given, normal acting in the upward direction, the force of friction in this direction, and the applied force in this direction. So of course, the roughness at the interface is being characterized by the coefficient of static friction. So higher this value means higher the roughness and higher the value of force. So force must be directly proportional to the coefficient of static friction mu s. And why this force is directly proportional to n as well? Because you see, the effect of n is to bring these contacting surfaces closer to each other. Okay, this normal force n is basically trying to bring these contacting surfaces together much closer to each other. You see, can you understand, can you realize the effect of normal force is to bring the contacting surfaces more closer to each other. So as the weight of the object increases, the value of n increases, and these two surfaces, the rough surfaces, begins to come closer to each other. And when this will going to happen, the roughness will try to penetrate into each other. Okay, this will create more locking effect, and ultimately it will going to increase the value of friction force. So it is pretty obvious, based on this observation and lot of experiments, that the maximum value of friction force is the product of coefficient of static friction and the normal reaction. But this is not an equilibrium equation, and in friction, in the problems related to friction, we need to use this equation many times, right? And so you see that since this equation is not an equilibrium equation, if you are using this equation in your solution, you have to show the correct direction of f in your free body diagram. Okay, you have to show the correct direction of f in your free body diagram if you are using this equation in your solution, because this is not an equilibrium equation. If you are not going to take care of this point, you might end up with the wrong answer. Okay, so I will going to stop here in this lecture, and in the next lecture we're going to discuss about types of friction problem and how to handle them. So until then, uh, good luck.